Okay, so sorry about that. I was trying to get my iPad to work so I can just work on the board, but I'm having some trouble. So I just have to show you the examples that I prepared. Can everybody just see me here? Okay. So in Castigliano's theorem, what we've learned is that if we would like to calculate the deflection, then the deflection is the rate of change of the elastic energy with respect to the force at a given point, and the deflection has to be in the same direction as the force itself, the same direction. It's very important. And if I would like to calculate the rotation at any point, then I take the rate of change of the energy with respect to the moment at that point. So the moment could be a torque or could be an applied moment. So these are the two basic equations that we would use. And then if we want to be specific, then we can look at every type of loading independently. So if I have axial loading, the energy, the elastic energy stored is F squared, proportional to F squared over AE, as we've seen. Then when we take the derivative, then I would have 1 over AE as a factor outside, and then I take the integral of F times dF by dFi dx. In other words, I must have an expression for the force system that is applied as a function of the force that I'd like to specify at a point I, and I take the integration. Similarly, if I want to calculate the deflection due to bending, then the deflection due to bending delta sub I, as you can see here, is equal to d by dfi of the integral of the m squared over 2ei dx. That's the energy u. So when we take the derivative with respect to fi, then I have 1 over ei m dm by dfi dx. Note here that this is deflection. I could also request that I'd like to get the rotation. So the rotation, for example, for torsion, it will be 1 over gj, and then I take the derivative with respect to the moment mi at a given point, or to the torque at a given point. That goes for torsion, and I can also calculate a similar rotation for bending by taking the derivative not with respect to fi, but with respect to mi at a specific point. So the bottom line is that these two equations here that I have, delta I and theta I, are general, and all what we need to do is find expressions for the elastic energy. So I was discussing in class an example, and the example had one shaft that had a second moment of area 2 times I1, and then a portion of the shaft had a second moment area of I1. So this is the BC section is fatter than the AB section. And then we apply the force at point A, and we wanted to find the deflection at 2 points, at A and at B. Obviously at C is 0, but at A and B. So we have to now look at A. We have a force F, and the deflection is going to be in the direction of this force. So I have to find the elastic energy in terms of this force, and then take its derivative with respect to this force. And as we saw here, that boils down to writing an equation that includes the product of m times the derivative of m with respect to the force. So I need to have two terms, m and its derivative with respect to force. So if I take this, and I integrate it. So I have one section, I do this integration of the two terms over AB, and integration of the two terms over BC. So over AB, it will be from 0 to L1. So the deflection here, delta A, is 1 over E. And then I have I1 inside, because from 0 to from 0 to up to the point B, which is L over 2, the moment is, the second moment area is I1. So I keep it inside the integral because it's a property of that region and space. So I have two terms. One is the moment itself, which is minus Fx, and minus is because the bending at this point here will cause the curvature to be concave, not convex. Concave curvature means negative moment. So minus Fx, and then when I take the derivative with respect to f, note that minus Fx, now I take the derivative of this with respect to x, with respect to f, I will get minus x. So these are the two terms that I have. And then I have another contribution to the deflection from L over 2 all the way up to L. And this contribution is now the moment changed to 2I1. So I have 1 over 2I1. And the moment is still minus Fx, because we're measuring x from this point. As one goes from A to B is still x, from B to C is still x. So it'd be minus Fx. And its derivative is minus x. And the integration of the first one, you know that we have x squared. So integration of x squared is x cubed over 3. So you get, and then you substitute for the limit L over 2, you get L cubed over 24I1. And then you do the integration for the second one, you get 7 over 48 of the same combination of parameters. And the final result is 3 over 16 FL cubed over E I1. So this is the deflection that we computed under this point. And in this example, there's only moments that we deal with. There's no axial force, there's no shear, there's no torsion. So the deflection is going to be following this equation, which is the contribution due to the moments, okay? Later, in another next example, I'm going to show you something that will have combination of axial and torsion and bending as well. So now we move on to finding the deflection at point B. And at point B, there is actually no force at this point. And I want to find the deflection downward at that point. So I now have to assume that there is a small force here, and this force is Q. This is a fictitious force. And then I find the moments, and the moment in this section and in this section, in AB and BC, the moment will have to be in terms of the force system. And the force system, in this case, I have two forces. One is F in here, and one is Q. So I must kind of consider both of them. So if I write now the moment in one equation, I can write it in two sections, right? I can write AB, and then section BC will be two different equations. But we learned that we could use singularity functions directly and write one single equation for the entire beam. So one single equation, it means that I have a concentrated force at A, so F is down at A, and then another concentrated force at B, which is Q, and then a reaction here at C, which I'm going to not include because I'm writing the moments from A to B and B to C. So the moment equation would be F, and F is negative, so minus F, and it is linear function, so Fx. But now I'm going to use the triangular brackets, indicating that it is a delta function at point x equals 0. And then I have another moment here, Q, minus Q, times another delta function, and the delta function would be x minus the position here. The position here is L over 2. And if we start from the Q equation, these triangular brackets will have a power of -1. But if we integrate it once to the V, then the -1 becomes 0. If we integrate it another time to the moment, the power becomes 1, linear. So if you look here now, the final equation, see, we can write it now. Once we understand these principles, we can write it in a simple way directly, even without starting from the Q equation, in one term. So we have m equals minus f times x, because this is the value of delta function is at x equals 0. And then I have the other second force is Q times its arm length is x minus L over 2. And then this term here is an activation of that at x equals L over 2. So we're activating the effect of Q at this position. So it is kind of raised to the power 0 because it's like a step function. So it's a different way of writing the moment equation using the singularity functions. In other words, I have two ways: either start from the Q and do the integrations, or can write it directly. One term doesn't have the triangular brackets because we know what it is, and another term is Q times x minus L over 2, but we just have to activate it at a certain point, and the activation is the unit step function x minus L over 2 to the 0. So now when I take the moment derivative with respect to Q, the first term is 0 because it doesn't have information on Q. The second term will be just x minus L over 2 negative, and then the unit step function is just there to show that the value is existent past x equals L over 2. And then when I do the integration, I have integration over two sections from 0 to L over 2. And in this case, I have only the moment is f minus fx, and its derivative with respect to Q is 0. From L over 2 to L, the moment is minus fx, and its derivative is minus x minus L over 2, as we have seen here. So this is the derivative with respect to the force Q. And doing this integration, we get 5 over 96 FL cubed over EI. So this is my example here that I wanted to complete, and I wanted to see if any of you guys have any questions. Do you still, everybody still can hear me? Oh, okay. So I guess one of you wants to see the last formula. So the last formula, I'll just go over it again. Let me expand this a little bit. Okay, so for part B, okay, so it's part B of the problem. I have the force that I'm going to put here is going to be Q, and Q is a fictitious force. So I will have this force to tend to zero. Let me see if I can comment here. Yes. So if you imagine that there's a force Q right here, then this force Q is going to be, at this point, I have a force Q, and the force Q is going to be a fictitious force that that will tend to zero. So if I have this force, I'm just trying to look for a way to draw free form. Yeah. Here is this force Q. So I have two forces. I have F and I have Q. One is at A and one is at B. So I have the moment now is F times X at any point plus Q times X minus L over 2. But this Q is activated only at X equals L over 2. So you have to have a step function, to a unit step function. So the result that we have is that we have here a moment equation that has the Fx, and then it has the Q times X minus L over 2. We take negatives because the curvature is concave, and the activation is a result of this unit step function here. And then I take the derivative of this equation with respect to Q, because I'm interested in the point B where the force is assumed to be Q. So when I take the derivative with respect to Q, then the F drops out and I still have this term. And then the deflection would be 1 over EI times the product of these two lines, M and the dm by dq. But since I'm doing integration, I have to integrate from 0 to L over 2, another integration from L over 2 to L. Is that clear, or do we have other questions? Okay. Well, since I don't have any response, I can't hear you guys, I'm going to just continue. Then what I would like to do is review another example, and this example will have a number of features that, let me try to get it here, that can have torsion and bending, and it's a little bit richer than the previous one, and will include several other features. So let's just see this example here. Okay, so this is the example that I wanted to discuss. And in this example, we have a wire, and the wire has a straight section, bent section, and a vertical section, and we're applying a force F on the vertical section at B, and we want to find the deflection at point B as a result of that force. So if we examine this problem, then I see that I have one section that is vertical from B to C, so I have to cut it here and look at the energy stored in B to C, and then another section from C to D. If I cut it here, I have to calculate the energy stored in CD, and then the section from D to G, I have to cut it and then calculate the energy stored in that section. Once I have the energy stored in terms of forces and moments and torques, then I can take the derivative with respect to this force F and find the deflection. So this is kind of a three-step process where we have to do free body diagrams for the BC section, the CD section, the DG section, and the free body diagrams will give us the required force system, meaning the actual forces and the moments and torques. And then we can calculate the deflection due to each component. So if we do that, the vertical section, if I cut it, then I've cut it at any point X, not at the bottom, but any point X. The bottom is A from the top, so if I cut it at X, then I have this force F must be equilibrated by a reaction VBC, which is the same as F from equilibrium, simple equilibrium. And I also must have a moment, and the moment is like a bending moment because this section wants to bend that way. So bending can be going this way. And therefore the reacting moment is MBC is going to be rotating in the counterclockwise direction. So the MBC is F times X. So that section here has shear forces on it, and it also has bending moment. As I mentioned in class, the contribution to the energy from the shear can be neglected, especially if it's a wire. If it's very thin, then I can neglect the shear. So we would just focus our attention on the bending contribution. So this is, kind of a simple system here. Let's just forget about these two. And this system, we can write an equation that the bending moment is F times X. And then when we take the derivative of Fx with respect to F, then I get X. And then I integrate and divide by EI. That gives me the deflection due to the energy stored in this section BC. And I integrate it from 0 all the way to A. And then I kind of store it on the side. So I solved maybe 1/3 of the problem, which is this one here. Now I need to determine what's going on for this middle section, CD. The middle section, CD, if I cut it to have a free body diagram, then I must add a horizontal force to counteract the applied force. And since the applied force is trying to rotate it clockwise, then I have to have a counterclockwise moment to react it. And the moment is F times A because F times the distance. This moment, in fact, because it is rotation around the axis of the wire, then we can call this moment very easily a torque. So this torque is FA. Not only that, but F, when it's multiplied by X, is going to rotate CD on the plane here in the counterclockwise direction. Then I must have a moment now, F times X, that is rotating clockwise. So in this system now, I have shear again, which I ignore. I have torsion, which I should take into account. And I have bending, which I should take into account. So I have a bending moment Fx. X now is measured from point C. So going back, because you have the freedom to choose any coordinate system, and we choose the coordinate systems that are convenient. So I'm measuring X from point C and moving that way. When I measure X from point C, I have the moment is Fx, and its derivative with respect to F is X, just like the previous case, and I can integrate from point C to point D. So this is one contribution. Another contribution is the torque. The torque is constant. Luckily, it's constant. Fa doesn't vary along X. And then when I take the derivative of the torque with respect to the force, I get A. And then when I do the integration along the section CD, the product of the torque and its derivative does not vary. And therefore, the integration is just the length of that section, which is B. So I will show you what I said in words here. So if you look at the torsion part, du by df is t dt by df over gj. And the torque is Fa. Its derivative with respect to F is A. And the integration gives us the length, which is B. So there's no integration here because the torque is constant. And we get this contribution from the torque. From the bending, very similar to the previous section, Fx times x integrated from 0 to B, and you get Fb cubed over 3ei. So summarizing, I have a straight section in bending only, and then I have a horizontal section, has bending and torsion. So two contributions, one bending, one torsion. And then the last section now is another section from D to G. And when I cut it to find the reactions, I have to counteract the applied force with the reactive force F in this direction. So I have an axial component now in this section. And then I have also a bending moment as FB. So I must compute the contribution to the elastic energy from the axial force, which is, I'm going to take the derivative, would be F dF by dFi. So obviously, dF by dFi is 1 because Fi is the same as F, essentially. So when I take the derivative, I get 1. So F times 1, it gives you F. The length is C, and then we have AE. So this is the contribution to the deflection from axial force on the section DG. Last is the contribution to the deflection from the bending section, from the bending, and the bending moment is constant FB. And when I take the derivative of FB with respect to F, I get B. And then I do the integration integration from 0 to C. Then I have these two terms, they add up like so. So as you can see, this is kind of this example shows that, number one, we ignore shear for thin wires. Number two, we have to take every section and do its contribution separately and write the equations for the bending moment and the torsion as appropriate, and the axial force. And then in some cases, these are constants, so the integration is just multiplied by the length. In some other cases, it's not constant, and we have to do the integration. Are there any questions, please? So, anybody has any questions? Because I'm not really getting any reaction. I don't know if people have any questions or anything like that. Or I'm not sure if I'm talking to myself because I can't hear anything. Okay, so since you still hear me here, I have kind of a cute example that will show you that things can get a little bit involved, not involved, just algebraically involved in some situations, and it is something that we discussed in class, like the example that I was trying to make up in the class. I have one that from the book Let me try to find it where we have even more things to kind of worry about when we have a structurally connected system, like a system that has some connections, like either cables or rods or things like that. So let me try to get it. Number 102 right here. So if I go to the problem set, and find the example here, or the problem set is 104, 102. So in 4, let's read it together, and then we try to learn something from it. So here's the problem. And the problem, there's a kind of a few examples that are similar. Like 101, you can see this example here. 102 is here. So let's see 102 and we think about it together. So 102, I have a force that is 2 kilonewton, 2,000 newtons at point A. Point A is 75 millimeter from the bolt. And then I have a bolt that is tight. And this beam here is held with the bolt. And then it is constrained from motion either up or down at point C. So we know now that the deflection at point C is, as a boundary condition, is 0. And then it is also tied to a bolt at point D. When it's tied to something else, as we discussed in class, DF is an external member that to the beam. So it's connected to the beam through some kind of force system that we have to obtain from a free body diagram. The same thing for DE. So there's a relationship between what's happening in the external bars and the force system on the beam A, B, C, D. Okay. So when we push down here, what's going to happen is that this bolt EB is going to react, so it's going to have a force in it. And the force in EB is going to extend the bolt, is going to pull it down. So the amount of extension depends on the stiffness of this bolt. So I know the deflection in the bolt is equal to the force divided by the spring constant, as we discussed in class. So now I have a connection between EB, the deflection in there, and the force. So there's a connection between the force at that point and its deflection through the effective stiffness of the spring. And this is another spring, so it has an effective stiffness. So it connects deflection to force. That's kind of the key point here, because we would like to determine the force reactions at EB. So there's a reaction here at C and at DE. So I have 3 unknowns and 2 equilibrium equations. Can't solve. So this is a statically indeterminate problem, as we discussed in class. So I have 3 unknowns and only 2 equations. Therefore, I must go to the idea of deflection. So when I have deflection, I have to find a deflection equation, as we discussed it. I write the moment using singularity functions, including this force, including this force, including this force, including this force. So this is 1, 2, 3. The fourth one, we can ignore it because it's the end of the beam. So basically, I have 1, 2, 3 concentrated forces giving me a moment that I can write an equation with that moment. And then when we write the moment, after we write the moment, then I can integrate it and find the deflections. And then deflections now are going to have the relationship between the forces and the constants of integration. So this is the idea. So if we look here at I'm going to just go over it a little bit quickly. I have the A, B, C, D, and this is the 2 kilonewton. I have one unknown F at BE, one unknown R sub C, one unknown as F at DF. This is the bolt force. This is the bolt force, and this is the reaction. And I know that the deflection at point C is equal to 0. So the procedure is I write a moment equation. First, from the equilibrium, I have two equations and two unknowns. Sum of the forces equal to the two applied here, or the sum of forces equal to 0 when you add the right sign. Take a moments about the end, then you get R sub C plus 2 FBE equals 6,000 newtons. So these are two equations, and I still have three unknowns. Therefore, I can write the equation for the moment using singularity functions. This is the applied force downward. This is the reaction in the bolt at 75 millimeters. This is the reaction at the support. And then I don't have another term for the reaction in the second bolt because it is at the end. And now integrated once, integrated twice with the EI, I get two constants, C1 and C2. So you can see now equation 4, I have C2, C1, R sub C, FBE, and so this is four unknowns. And then I also have FDF, which is at the end. So it's 5 unknowns. In order for me to find I have two equations, 1 and 2. I need 3 other equations from the deflection equation 4 to generate 3 other equations. And that is the boundary condition here at the bolt. So at the bolt I know the deflection is related to the force. At C, the deflection is 0. And at D, the deflection is related again to the force. So it's a little bit indirect at B and C because we have the force relationship. At C, deflection is 0. So if we write these conditions here, at B, the deflection is minus FL over AE. This is F over K. K is AE over L. So this is a known thing, and therefore it is the deflection is related to the force. And I substitute that into equation 4, gives me a specific form that is in equation 5, as you can see here. And at X equals 150 millimeter, then the deflection I know for sure is equal to 0. And I substitute that, I get another equation 6. And finally, at the end, the other end, the deflection here is F over K effective, which is FL over AE. And that brings in another relationship with the force. When I put this relationship in the general deflection equation 4, I generate the last of the set of equations, and that is in 7 here. So you can see now I have 5 equations and 5 unknowns, very lengthy process, and I can now solve them using a matrix solution. This is the linear system of equations. This is the matrix of coefficients. These are the unknowns, R sub C, FBE, RDF. These are 3 forces and 2 constants of integration from the deflection equation. And this I can use MATLAB. If you just build the matrix A in MATLAB and the force vector F or the free vector F, then by inversion, it's one simple line in MATLAB, you get the results, as you can see here. So for us, in any exam or anything like that, we are not going to really require a solution to that system because it's just a matter of putting the numbers. But we would like you to understand how to build the set of equations from the boundary conditions. That's all what I have here, and I wanted to thank you for attending, and I wanted to see if you guys have any other questions before we stop this session. Okay, so it seems like I don't have any questions. I think we're going to just stop this session, and I'm going to try to post it online, and we'll see you then next time in class. Okay, bye-bye. Take care.